Okay, good afternoon, everyone. Hello. Hello. Okay. I see the 10 students. It's 10 students now in the in the room. So we may wait a few more minutes. Okay. So other students are joining. Okay, I think other students are joining and will join the afternoon session. So well, without further waiting, so we start the this afternoon session. So this morning session, so we introduced the time area method, and also I also show you some example, and also you already have a practice, okay, an exercise for time area method. So the time area method actually is used to estimate the inflow rainfall hydrograph. Okay. So, but because for the basin design, for the detention basin design, actually we use two hydrographs. Okay. Actually, I show you in the previous slide. One is the inflow hydrograph, one is the outflow hydrograph. Okay, so with these two hydrographs, we can determine the size of the detention basin, and now we can also check whether our outflow, the peak outflow is lower the pre-development flow rate. Okay. So next we need to talk about the routing. Okay, the routing. So the routing actually is used to find out the outflow hydrograph. And also the routing also depends on the different outlet arrangement of the detention basin. Now step 3 for the detention basin. Step 3 is about the stage and the storage relationship. Means the stage and the volume. The stage and the volume relationship. Okay. Normally, this is a ratio between the depth of the water in the basin, and also the volume of the water in the basin. Okay. So actually, normally we can use the integrations to find the volume. Okay. For example, we can use the these integrations to find out the volume of the basin. Okay. Now we can separate it into we can divide the basin at different intervals. For example, at 1 meter intervals. Okay. To the integration actually is usually done numerically. It's usually done numerically, as basin geometry is typically irregular. So normally the two rules we used, one is the Simpson rules, another one is trapezoid, the trapezoidal, another one trapezoidal rules. Okay, trapezoidal rules. So actually, for the Simpson rule, actually we use the parabolas. We use the parabolas to approximate each part of the curve. So this proves that to efficient. Okay, but actually it is more time consumed. Okay, by using the Simpson's rules. Now for a simple method, okay. Now the trapezoidal. So the trapezoidal rules is normally used. Okay, so as listed here. Okay, as listed here. So we use straight lines to model the curve, and learn towards improvement over using rectangles to finding the areas. Okay, on the curves. Okay, so that means we can separate. So we can divide it. Right? Okay, divided the basin into different levels at different levels. Okay, so for example, start from the base to the top. So from bottom, from the bottom to the top. So we can start from, for example, from the 0, and at 1 meter intervals, we can get the area at each level. Okay, you can get the area of each level. Okay, for example, if we have the from 10 to 15, okay, the area. If we get the area from the bottom to the top, so we can have the volume by using the trapezoidal rules. Okay, so this one is the Now this is the trapezoidal rules. We can get the volume. So we can get the volume of the detention basin. Okay. So we can get the relation. So we can get the relation between the stage and the volume. Stage and the volume relation. Now next we initial estimate of the basin properties. Initial estimate of the basin properties. So the for the concentrated storage, the peak of the outflow hydrograph has to be on the falling limb of the inflow as required for the concentrated storage. Means for the concentrated storage, so this the outflow peak. So the outflow peak on the falling limb of the inflow, on the falling limb of the for the inflow on the falling limb of the. Actually, it's easy to understand. Okay, because the accumulation of the storage continues. So these two curves will meet. Okay, will meet. So after the intersection point, so the outflow curve is above the inflow curve. You can see after this intersection point, so the outflow curve is above the inflow curve. So that means the the water released from the storage, okay, means the water withdrawal of the water from the storage. It means the water releasing from the storage is larger than the water flowing into the storage. So that means the water level in storage decreases. Means the water level decreases in the storage. So that means the outflow rate also decreases. So it is understandable. So that means the storage in the basin. So the storage in the basin will be maximum at the intersection point. Okay, because after the intersection point, so the water the outflow is larger than the inflow. Okay, so that means the water level in the basin will decrease. So that means the outflow rate will decrease accordingly. For outflow is unregulated, so the discharge is the maximum when the storage in the reservoir is the maximum. Okay, that's very easy to understand, right? Okay. So therefore, for the unregulated concentrated basin, so the peak outflow always at the intersection point. It is not true for the channel routing. Means for the routing of the channel, of the open channel. So actually, in practice, we need to know the criteria. In practice, we should have the QP less than pre-development peak flow rate. Okay, so that means from the rational method. So this is one criteria. Remember, okay. So the outflow, the peak of the outflow QP should be less than the pre-development peak value, peak rate of from the rational method. So that means the outflow rate of from the detention basin should be less than the runoff of the natural catchment. Means less than the pre-developed natural catchment to reduce the risks for floodings of the downstream areas. So in doing so, if there's not enough storage in detention basin, so we need to adjust. We need to readjust the size of detention basin. So it means we need a larger. Size. Okay, larger size. Okay. So how to calculate the maximum value of the temporary storage, the memory? So we use this equations to find out the maximum volume of the temporary storage. So that means the size of the detention basin should be larger than SP, should be larger than SP. So SP means the maximum volume of temporary storage. So QP is the peak discharge of the outflow hydrograph. So IP is the peak discharge of the inflow. IP is the inflow. High peak discharge of the inflow. So that means this is not at least here, but I can draw that. So this is. So this is sorry. So this is the IP. Okay. 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 So this is IP. This is IP. This is IP. So the IP is the peak discharge of the inflow hydrograph. So here's another one, V in. V in means the total volume of the inflow. What that means, the area under the inflow hydrograph, the area means the area. Okay, so this area is the inflow volume, total inflow volume. So by using this equations, we can get the maximum volume of the temporary storage. Okay, for the design rainstorm. Okay, so that means the detention basin should be larger than the size should be larger than the SP. So this is the detention basin. Okay, the discharge, the stage and the discharge relationship. Okay, there are different kind of the outlet structures. Could be open channel, orifice, PEP, or we can use multiple outlet. Means they could be combinations of the pipe and pipe and for example the weir, and also the broad crested weir. So the broad crested weir actually normally used for the major event, major storm event. For the spillways, actually is used at the spillways for a major event, and it covers. So the outflow of some stormwater runoff storage facilities actually impacts the downstream properties. Okay, and the receiving water bodies. So the location of the outlet structure is therefore is important in design of an stormwater measurement system. So the outlet from a storage facility should be located to assess the near natural drainage feature, so which can convey the release flow from the storage, so which has the adequate capacity to convey the flow from the basin. And also I mentioned that the overflow and the emergency spillways means normally the crested weir, the broad crested weir, normally is designed to accommodate a major event, normally for a 100-year 100-year storm. Sorry. So the spillway actually should not design to discharge towards any downstream structures, because this spillways water normally indicates a major large event, a major large rainstorm event. Okay. So actually, this slide is showing the difference of the open channel orifice and PEP. The difference, you can see that. You can see that. So you can see that for the open channel, actually you can see that is it's called filling. So that means the inlet, the water level is lower than the upper word of the PEP, and of course the same for the outlet. The inlet and outlet, the water level is below the upward of the pad So the HGL, the hydraulic grid line, is the same of the water line. It's same with the water line. Okay, same with the water water level. Now for the orifice, orifice actually is the inlet, only the inlet submerged. So that means this inlet submerged, okay, submerged, the inlet submerged, but the outlet not submerged, not submerged. So in this case, also the HGL is also the same. In the PEP, the HGL is the same with the water level in the PEP. So actually, you can see that the, for the orifice flow, actually only the inlet submerged, but for others, you can see not submerged. The last one is the PEP flow. The whole cover submerged, including the inlet and outlet. Okay, inlet and outlet. So in this case, you can see that the HGL is higher than the upward of the PEP, upward of the PEP. Okay. So that means what that means the water in the PEP has on pressure. Okay, on pressure. Okay, so this is the different 3 channels. Actually, we'll use different equations for this 3 different outlet structures. Now for the open channel, okay, so this slide showing the open channel, we use the Manning's equation. Actually, we already talked about that in the rational method. Okay, for the rational method, actually we need to determine the times of contraction. So we use the Manning's equation. Open channel, as I mentioned, that the water level, the inlet is not submerged. Okay, it means that here is not submerged, and also the outlet also not submerged. Okay, not submerged. Actually, this figure showing a typical detention basin. So this is a lower outlet, this is the upper outlet, and also you can see here is a emergency spillway. Okay, so this is a typical detention basin. So open channel, using the Manning's equation. So actually, I think it's easy to understand. Okay, so the open channel actually is a lower part of the flow to be exposed to the atmosphere. Actually, it means normally the pressure is the atmospheric pressure. So actually, this type of channel actually includes the river, covers, stormwater system flow by gravity, and also roadside ditches and roadway gutters. All these are the open channel. So proper design requires that open channel have sufficient hydraulic capacity to convey the flow of the design storm. And also open channel assume the pressure at the surface is constant. Okay, it means no change. Okay, the pressure at the surface is constant, and the hydraulic grid line is at the surface of the fluid, as I just showed you. Okay, the hydraulic grid line is at the surface of the water. And also the water level is lower than the upward of the outlet. It's lower than the upward of the PEP or the covered. Okay. So in this equation, actually, I remember I mentioned that already. So the A, I just want to repeat that again for your easy reference. So A here is the cross-section area of the open channel. For example, for the PEP, for the round shaped PEP, so it is the cross-section area of the open channel. N is the Manning's roughness coefficient. I already mentioned that actually it's not dimensionless. Actually, this Manning's roughness coefficient, so has a unit. R is the hydraulic radius. Means the area, means the cross-section area of the water over the wetted parameter. So S is the slope. S is the slope of the channel or gutter. Channel gutter. Now for the off-phase outlet means it's also freely discharging, called free discharging, but the inlet is submerged, inlet submerged. Okay, inlet submerged. So an orifice actually is always control, outlet control. So that is typically applied to bioinfiltration or bioretention basin, wet basin. Okay. So the orifice actually is suitable for the stormwater measurement. Okay, for any size. The head water actually is above the upper verge of the pipe. Okay, actually, because the inlet at the inlet the inlet is submerged. Okay, is submerged. Okay, but the exit is not submerged. The exit is submerged. Is not submerged. So the normal depth of the water in the pipe is less than the diameter of the pipe, as I show you. Okay, the depth, the normal depth of the water in the cover is less than the diameter of the pipe. So that means the water in the pipe is not under pressure. It's not under pressure. So here we also develop the orifice outlet equations from the Bernoulli, based on the Bernoulli energy equation. Bernoulli, I just mentioned that. Remember? Okay, this is the Bernoulli. This is the Bernoulli energy equilibrium. Energy is called Bernoulli energy equation. So what that means? That means for I just to repeat again, in the steady flow. Okay, in a steady flow, so the sum of the pressure energy, kinetic energy, and the potential energy remains constant at any section if no energy is added or taken out. Okay, so that means the pressure energy, okay, the pressure energy and potential energy and kinetic energy. Okay, P, the P over rho G and is the pressure energy. Okay, pressure energy Z represents the potential energy. So the V square V over 2G is the kinetic energy, means due to the movement of the water. So at any section, so this the sum of these three types energy is a constant. So that means P1 over rho G plus Z1 plus V1 squared over 2G is equal to P2 over rho G plus Z2 plus V2 square over square meter over 2G is constant. Is constant. So we can get the orifice equations very easily, and because the pressure no change. Okay, pressure no change. Means at the inlet and also the outlet, the pressure the same. Okay, the pressure no change, and at the inlet, we assume the velocity is what? The velocity is zero. Okay, it's zero. It's zero. Okay, so that means the P1, the P2, P1 and P2 is the same. Okay, and also the inlet is zero. The V1 is zero. Okay, so you can see that it is what? It is the only the Z1, Z2, and the V2 square over 2G. Okay, how about the Z1, Z? Z I just mentioned. Z is the potential energy. Okay, potential energy. So that means you can move the Z2 to the left side. Move the Z2 to the left side, so you can get Z1 minus Z2. Z1 minus Z2 is what? It's the head. HOO. It's the head. It's the head loss. Okay, so the head loss of the water, because at the inlet the water is higher than the outlet. Okay, so there'll be head loss. The head loss actually is the difference of the potential energy. Potential energy. The change of the potential energy is the change. So the head loss is the change of the potential energy. So HOO is the head change. Okay, so move to this side is HOO. So you can see V is what? V is 2G HOO square root. Normally we will times a coefficient, orifice coefficient, orifice coefficient, orifice coefficient. Okay. Actually, the coefficient actually depends on the from 0.6 to 0.9. Actually, this depends on Reynolds number and D over HOO and also the geometry. So this is the orifice outlet free discharging. Okay, free discharging, but the inlet submerged. Okay, any questions? Have? Now next is the PEP flow. Now for the PEP flow, actually, the outlet of the PEP is submerged. So the normal depth of the water in the cover of the PEP is greater than the diameter of the PEP. And show in the previous ones. So the let me see this one. This one. So this one, the last one is the PEP. So in the PEP, we can see that the outlet. So we can see the this is the PEP flow. PEP flow, we can see that the outlet, the inlet submerged, the outlet and submerged. Okay. And also the HGL, the hydraulic grid line. So the hydraulic grid line is higher. Okay, it's greater than the diameter of the pipe. It's greater than so that means it's under pressure. The water in the pipe actually is under pressure. So actually, this one is also based on the Bernoulli equation. Okay, Bernoulli equation. But we need to consider for the PEP flow, we need to consider the two energy loss. We need to consider also. Okay. So one is the this is the friction loss. Friction loss. And another one is the Manor loss. Another one is the Manor head loss. So this one is the Manor head loss. So we need to consider the two energy loss of the PEP. So to minimize the head loss in the PEP flow, so the selection of the PEP material and the joints are very important. Okay. So the resistance in the PEP actually will be influenced by the material used for the PEP. Okay. And also will be influenced by the sediment on the PEP surface. Okay. So all this causes the friction loss. So this one is the friction loss we use to this one is the we use to calculate the friction loss. So the other sources of energy loss actually include the entrance, exit, bends, joints, valves, manholes, and other fittings and obstructions. So all these other sources of resistance, so we refer to as the Manor head loss. So here's the Manor head loss. Okay. Actually, the key actually is a factor. Okay, we can find out in a table. So that means for the PEP flow, we can also use this energy equations, the Bernoulli energy equations, means the total energy is unchanged. Okay, unchanged at any section of the flow. But we need to consider the frictional energy loss and also the Manor head loss, friction loss and head loss. Now for the PEP outlet, commonly used as a low flow outlet. Okay, low flow outlet. So the head losses are divided from the friction and the Manor loss in the PEP. Okay. So this is the head loss. I just mentioned the first part is the friction loss, and the second part is the Manor loss. So as I mentioned, K is the coefficient K. So K is the coefficient actually of the other sources of the energy loss, such as at the entrance, exit, the bands, joints, valves, manholes, and other obstructions. Okay. So normally for the key, we consider the two losses for key. Normally the key we can take 1.5, 1.5. 1.5 include entrance loss and exit loss, Okay. So in this case, the metal loss are at the entrance and the exit if there are only one path. Okay. So the entrance loss normally we take at 0.5, and the exit loss so we can take the coefficient 1. So you can see that the total metal energy loss is 1.5. Okay, the coefficient is 1.5. So after this one, we can get out so we can find out we use the energy loss, we use the head loss, we use the head loss, we can get the energy flow, so we can get the PEP flow here, we get the PEP flow here. Based on the head loss from the friction and the metal loss, so we can find out the PEP flow rate. That means the flow rate in the PEP, Okay, flow rate in PEP. So these are the three different equations we used for the open channel or orifices and also the PEP outlet. So any questions you have? Okay. I think all of you are no questions. Okay. Oh, next one, we also introduce another structure. It's called broad crested weir. Over the spillway. Actually, normally functions as an emergency spillway, for a major event, for a major rainstorm event, normally for 100 years rainstorm event. Okay, so that means the water level is in the basin is above the weir. It's above the weir. Okay, means it is higher than the depth of the basin. Okay, so we'll use the emergency spillway. But how to calculate that? I don't know why here it looks cannot show correctly. Okay. Let me check. Maybe I show you another one. Yeah, maybe I show PDF versions. I'm not sure. Because this, I made some update. I made some update because the previous one there's some kind of confuse of the of the term used. Okay, of the term used because I want to make it clear of the term used because the coefficient in the previous versions that we use the weir coefficient actually not, it is not correct, I think. After checking the relevant references books. So okay, let me check in the PDF versions. It's okay. Yeah, the PDF version is okay. Just wait a few minutes. I changed the PDF versions. I think I need to upload first. And then we need to wait well. So the broad crest weir actually are commonly used as the overflow spillways coming to effect for very large rainstorm event. Okay, normally it happens we use the ARI, and it's average recurrence interval. For example, we use at 100. So actually, the emergency spillway actually normally is included in the stormwater retention basin design, okay, to safely pass the extreme flood flow, flood flow. So the spillway actually prevents the pond water levels from overtopping and from overtopping the and also causing the structural damage. So actually, this emergency spillway must be designed to convey a 100-year stormwater event, okay, and also located so the downstream structures will not be impacted, okay. I will change it to the PDF file. Let's see whether it is okay. 67. Okay, it's good. It's okay now. Okay. Now I change it to the PDF file. Now it looks okay now. Okay. Actually, here I listed two equations to calculate the broad crest width outlet. But actually, these two equations are similar, but the difference is use different discharge coefficient. Okay, because before in the older versions here it is called the width coefficient. Actually, after further checkings, I found that it's not correct, so we changed that to the discharge coefficient. Actually, both these two are discharge coefficient, but they are different. So this one I can see I use CD, a different code, okay, to represent the discharge coefficient, okay. But these two both can use to calculate the broad crest width outlet. So for the broad cross width, okay, so you can use this one or use this one. So actually, these two are quite similar. Okay. For example, for the broad crest width, normally the HOW is much less than the storage depth. So the CD is 0.577. So what that means? So that means this equals to the y W over H, y over W over y over W, YW over H is quite close to 1. It's quite close to 1. Okay, so that means this this figure could be around the 0.85. 0.5. Okay. So 0.85 times 0.385 is what? Is what? Let me check. Let me see this one. Okay, yeah, actually, after the calculations, actually these two coefficients are actually very, I think it's very close, Okay, so be careful. This in these slides, I made updates. Okay, just because this the CD actually is, we call it discharge coefficient. So actually the CD actually these two CDs are different. Okay, these two CDs are different. Okay. Let me see. So the weir actually normally is a long rest channel across the crest section. Actually, it's normally we call it a broad crest weir. Actually, the weir can have different shape, triangular, trapezoidal, or circular. Okay. Actually, the broad crest weir flow normally that means the crest length means the head above the crest is between the limits about 1/20 to 1/2 of the crest length. Okay. So the energy loss actually over the weir is not negligible. Okay, and the estimate of the flow rate must be corrected to account the energy loss. So that's why we use the discharge coefficient. Okay. So the discharge coefficient actually now is used here because the energy loss over the weir. So actually, you can see that on this slide, the different discharge coefficient, the different discharge coefficient used here. Okay, but it could be similar. Okay, the results actually could be same. The result the same means the coefficient could be same. Sorry. So you need to pay attention. Is actually use the formulas given in the final assessment papers. Okay, normally the equations used will be provided. Okay, at the end of the assignment papers. At the last page of the assignment papers. Okay, so normally use the equations given in the assessment papers. Okay, in the assessment papers. Okay, so actually in the previous slides, actually there's two equations used, but actually the result could be similar. Okay, so when you attend the final assessment, so use the equations provided in the final assessment paper. So the step 4 is the stage in the discharge relationship. Okay, so here we need to spend a bit time to discuss. There are three types. Actually, this is for the submerged entrance conditions only. So what that means the inlet. So the inlet is submerged. The entrance is submerged. So be careful here. This is only for the submerged entrance conditions, type 1, type 2, type 3. Okay. In type 1 and type 3, in type 1 and type 2, is submerged actually. We can use the type 1. Okay, and also the if the covered or pipe exit is submerged, so then the flow type 1, and also the discharge is given by the equations. So this both equation. Okay, if the submerged, okay, in type 1, if the exit, you can see the exit is also submerged, so we can use this two. One of these equations. Okay, so we can use this one. And also we can also use this one. Both okay, the same result. And also next, if the covered exit is not submerged, if the not submerged, actually we may consider the type 2 and the type 3. Type 2 and type 3. So firstly, we assume the flow is type 2. Firstly, we will assume the flow is type 2 and calculate the discharge using the equation 1 or 2. So we can use the flow rate to determine the normal depth of the flow in the cover. So that means after calculation we can get the Q, right? Okay. So after get the Q, can over the we can get the normal depth. We can get the normal depth of the covered. Okay, of the covered. So if the normal depth, okay, so if the normal depth is greater than the height of the covered, is greater than the covered, it means it's greater than, for example, if there is a circular, if greater than the diameter, so the flow is type 2. We can confirm that the flow is type 2. The flow is type 2. So the discharge, so the discharge calculated is correct. We calculate is correct. The discharge we calculate is correct. Is correct. So if the normal depth is less than the height of the cover, the normal depth is less than the cover or the diameter of the pipe. So then the flow is probably type 3. Type 3. So the type 3. Type 3. So we calculated so then we calculate the discharge by using the equation. By using the type 3, means use this one. Then we calculate using this one equations, okay, and verify the normal depth is less than the cover height. So if the normal depth is less than the cover height, then type 3 flow is confirmed, okay. But if neither type 2 or nor type 3 flow can be confirmed, so we take the capacity of the covered to be the lesser of the two calculated discharges. So that means we use the capacity. So we use the capacity. We use the discharge with a lesser, with a smaller one. So we choose the discharge with the smaller one. And also, be clear that here, for the circular cover, I mean the circular pad, for example. Okay, for the circular covered flow, actually, the flow full when the discharging rate exceeds 1.07 Q full. Q full means what? Means the full flow discharge using the Manning equation. So we can use the Manning equation to get the Q full. Okay, means the full flow discharge of the pipe. But when we consider the pipe is fully discharging at a fully discharged rate, so that means we can times the 1.05. Okay, times 1.07. So 1.07. So that means if the discharge rate is exceed 1.07 times Q full, so we can say it is type 2. Okay, we can say it's type 2. Okay, type 2. Okay, okay. But if it's less than the 1.07 times Q full, we still can state as a type 3. Type 3. Okay, so this is the three types. The three types. Three types of the dischargings. Three types of the cover flow dischargings calculations under the submerged entrance conditions. Okay, so I just summarize that. Okay, so the for these three types, okay, you can see that the first type 1, the inlet and outlet both submerged. So we can use this use type 1 and type 2 equation to calculate the discharge rate very easily. Okay, if the exit is submerged. Okay. So, but for the type 2 and the type 3, we need to check. We need to check the normal depth. We need to check the normal depth. Okay. So if we assume it is type 2, we after calculation we get the Q, and then we get the normal depth. Normal depth is yn. So if the normal depth yn is larger than the d, d is the depth of the cover, so it is type 2. If it is less than, if the normal depth is less than d, so it is type 3. So we need to check. So this is the coverage under the submerged entrance conditions. Okay, actually later on I think there'll be still an example. There'll be still examples to show you of this case. Actually, this are the I just talked about this slide showing what I just said. Okay, so for the submerged entrance, so the flow is either type 1, type 2, or type 3. Okay, you can follow the following steps procedures to determine which it is type 2, or it is type 1, or it is type 2, or it's type 3. Okay, now for the circular covers, okay, means the cross section is circular. You may be careful here. That means the full when the discharge rate exceeds 1.07 Q full, we consider that the circular covered flow is full. Okay, this is one you need to pay attention. And also, as shown in the previous slides, you can see that actually multiple outlets. Actually, normally for the detection-based design, we use the multiple outlet. We use a lower outlet, and then we have the higher outlet, and also we have the spillway. It is very common for a basin to have more than one outlet. Okay, the outlets are placed at different levels. Different levels. So also be careful to ensure that the state discharge relationship accounts for the invert levels of different individual outlets. So that means you need to see the stage and the discharge. The stage and the discharge, the curves will be different for the outlet for the multiple outlet basins. And also in the outlet, okay, normally in the outlet, for example, in the lower outlet, normally the bars or grills are normally used over the entrance, okay, to prevent any blockage, okay, okay, for safety reasons also, okay. So for low flow outlets, normally the bars, grills are placed over entrance for safety and to prevent the blockage of the outlet. Okay, so actually this will increase the minor loss at the entrance. Okay, and I just show you the minor losses in the entrance and the exit. Normally we take it at the entrance we take it at 0.5. At the exit we take it at 1. The coefficient. So this is the let me see. This is the this figure showing showing the multiple outlet stage and the discharge relations. Okay, stage and the discharge relationship. Okay, so for example, you can get this is the you can see that from the depth from 0 to 1.2 diameters. So it is the artificial flow, and above that you may consider the full conduct flow. So above the weird, we'll use another weird flow equation curve. Okay, so we have three different curves because with from 3 different equations. So the first one is the average. So the second one is the pad. So the third one is the weird flow. Okay. So multiple outlet. Okay, so so most commonly there are 2 outlets used. Okay, mostly commonly there are 2 outlets are used for the multiple outlet. One is a low flow outlet. For example, this is the orifice or pad. Another higher flow outlet means the broad crest weir. So here is examples of combine of the orifice and the weir outlet. So this is means the outflow actually include the flow in the cover and also the flow the spillway, the flow in the of the spillway. Okay, so that means this is the total outflow. The total outflow is the from the orifice and also from the weir, from the weir. Okay, from the weir. Okay, now we stop here for because next we will introduce the questions. And also here is we can have a poll here, and then when you give the polls, we can take a rest. Okay, the poll. Let me see. What's the poll? Oh, this one. I have the poll to make sure you understand the three types of the cover. Three types I just mentioned: tab 1, tab 2, and tab 3. Okay, if the entrance submerged. Okay. So this tab actually we that means the entrance submerged. Okay, entrance submerged. Entrance submerged. Let me see. Is the covered is the entrance. Let me see. Wait a minute. Okay, it's clear now. It's a word limit using the poll. Okay, here's the poll, and also we take a rest. Okay, have a rest break. The back end. Let me see. Okay, and also here's a poll. Okay, here's a poll. Here is to check whether you're understanding what have mentioned just now. Okay, about the three types of the flow of the if the entrance is submerged. So what is the and also the exit is not submerged. The normal depth is larger than the height of the cover. So the flow is tab 1 or tab 2 or tab 3. Okay. And also we have a short break. Okay. So for 10 minutes. Okay. Now see it is 2:34 or 35. 35. So we have 10 minutes break around. Okay. And also at the same time you can give your response to the poll. Okay. Okay, after a short break, we'll continue this afternoon workshop. So for the questions, I just post in the post the covered entrance is submerged. Okay, and we just talk about that. So the exit not submerged. Okay. So if the exit not submerged, actually, so that means it cannot be type 1. Okay. The type 1 actually is the entrance. The exit is submerged. Okay, it is type 1. So actually, it should not be the type 1. So we need to check it is type 2 or type 3. Now then we can see that the normal depth is higher than the height of the covered. Okay, so then that means what? That means it is type 2. Okay, it's type 2. Okay, not type 3. Not type 3. Okay. Next one is example in the textbook. Actually, example in the textbook. Let me see. Maybe you can just to do the exercise first. Not yet. Okay, we'll show the example first. Okay. Actually, this example actually is about the concrete box cover. Okay, so the it is 1.22 meter times 1.22 meters. The cross section is a square. The n is 0.013, and also the entrance is with a rounded entrance. Okay, so the key 0.05, and also CD is 0.95. So the cover slope is 0.5%. The length is 36.6 meters. The head water is 1.83 meters above the covered invert. Okay, so consider the following cases. A, free outlet conditions. Okay, and the B, the till water elevation 0.304 meters above the top of the box at the outlet. Okay, and what must the head water elevation be in case B for the cover to pass the flow that exit in case A? So this question is actually the first part. You need to determine the flow. Okay, the capacity. Okay, the capacity of this is covered. So I can see that the entrance is submerged, right? Okay, the entrance is submerged. Now for the A, we can see that this is free outlet conditions. Free outlet condition, actually that means the exit is not submerged. The exit is not submerged. So we need to think about is type 2 or type 3. Type 2 or type 3. Okay. So we use the type 1 or type 2 equations. Okay. Now we use these equations. Okay. Okay. Use equations to. You can see that. Okay. For the free outlet conditions, 2 types of flow are possible. Means the type 2 or type 3. So firstly, we assume the is type 2. Okay. We assume it is type 2 flow. Now we use the flow rate equation here. Okay. We use the flow equations here, or use these equations. Okay. Now we need to determine the head change and also the roughness coefficient given, the length is given, and also we need to determine the hydraulic radius. So hydraulic radius is what? Is the area. Is the cross section. Is the cross section area over the wetted parameter. So in this questions, okay, the R. So the hydraulic radius is 0.305 meter area over the parameters. And then we use the equation to find out the flow rate as 4.59 cubic meter per second. So next step we need to check the normal depth. Okay, we can use the Manning's equations. We can use the Manning's equations. So of course we can use the Manning's equation to get the full flow. Okay, the full flow is the 3.67 cubic meter per second. So you can see that 4.59, and so the discharge is 4.59, is larger than the full discharge, and so that means actually based on this we can see that the normal depth is larger than the depth of the cover. So here is another method. Okay, we use the where n normal depth. If the normal depth flow is where n, so we can calculate the area, we can calculate the parameter, we can get the radius. Okay, hydraulic radius. So we can use these equations to calculate and get the normal depth. Look at the normal depth. So you can see the normal depth is 1.25. 1.25. So 1.25 is larger than 1.22. Okay, the height of the cover. Okay, so that means the type 2 flow is confirmed. Type 2 flows, but this one I think is it would be complicated to use this one to calculate the normal depth. Okay, but you can use the full flow, rate. Okay, you use the Manning's equation to get the full flow rate. So compare the discharge of the covered. If the discharge is larger than the full flow, so that means the normal depth is higher than the depth of the cover. So in part B, actually means the tail water is what is 0.301 above the cover outlet. And therefore the difference in the water head is what is the difference between the inlet and outlet. So that means it is this one. So actually it is type 1 flow. Type 1 because the exit is submerged. Okay, the exit. So we can use the equations to get the discharge rate. Okay, see the discharge rate is 3.6 cubic meter per second. So you can see that. Okay, when the tail water depth rise, the tail water depth rises to 0.305 meters above the cover exit. So the discharge rate decrease. Okay, decrease. So next one, we need to make sure that the discharge rate is also the same. At the tail water is the same. Okay. So what is the head water? What is head water? We can assume that the head water acts above the covered inlet. Okay. And also the tail water is 0.305 above the outlet. So firstly we can get the head changes. So we can use the type 1. Head change can use type 1. So we can find out the x. So the x is 0.915 meters. So that means if the head water depth at the entrance is 2.14 meters, originally you can see that the head water is 1.83. 1.83. So that means now, okay, if the head water depth is 2.14 meters, so the discharge, rate will be keep the same, 4.59 cubic meters. Okay. So actually, this example using the of the entrance submerged covers. Okay, there are 3 types conditions we need to know. Okay, 3 types conditions we need to know. Now, before we move into the hydraulic routing, so I think we have some examples here. Okay. Let me see which questions we have. 6, 7, 8, 9, 10. Okay. Okay, let's have a look. Now, question 6. Okay, start off with, now first we have a look of the question 6. Now, question 6 actually is a 45 cm diameter the concrete covered drains storage basin. The entrance is shaped, so the CD is 0.8, and estimate the basin discharge when the water is in the basin is 1.1 meter above the center of the covered entrance, and the cover is discharged freely into a drainage channel. So from this one, we can see that the cover is discharging freely into a discharging channel. So that means the exit is not submerged. Okay, the exit. So this is not tab 1. So it will be tab 2 or tab 3. Okay. And also the basin. So you can see the whether it's entrance submerged. So the entrance submerged means this H over D is larger than 1.2 D. Okay. I just show you. Okay, if the H over D is larger than 1.2, so we assume that it is the entrance is submerged. Okay. H is the depth. H is the depth of water in the basin. Okay. So D is the height of the lower outlet, the height of the lower outlet or structure. So in this question, I think this is the, so you can see that the water level is the 1.1 meter above the center of the cover entrance. So that means the depth of water is 1.1 plus the radius of the covered. Okay, so actually you can easily see that it is the H over D is larger than 1.2. So that means so you can see that the entrance is submerged, but the exit is not submerged. Okay. So let's see the solutions of this question. Now this is the questions. Okay. So so the center of the from the pipe to the water level is 1.1 meters. So actually we can get the H is 1.1 plus 0.45 over 2. Okay, so we can easily find the H over D. H over D is larger than 1.2. So that means it is submerged. Okay, submerged. Entrance submerged. Okay. And also the exit is not submerged. Okay, the exit is not submerged. Okay. So in this case, I think we use the orifice. Okay, we use orifice. Let me check. And also another things we need to know about that is the discharge. Okay, the cover is discharging freely into a drainage channel. So that means the exit. So the exit is not submerged. And another one we need to another information we can get is that it is the water is not under pressure. Okay, so the water in the pipe or in the covered is not under pressure. So that means it is we can consider if it is freely discharged into a drainage channel. Actually, it is we can consider it is a orifice flow. Okay, so that means we use the equations, type 3 equations. We use the type 3 equations, so we can get the flow rate. So we can get the discharge rate of this covered. So finally, you can get the answer here. Okay, so this question actually is easier because it is tab 3. Okay, tab 3. Okay, tab 3. So now now here you can see that you need to get the information from the questions. The covered is discharging freely into a drainage channel. So that means it is there are two information you need to get from this questions. One is the exit is not submerged. Another one is the it is tab 3. It is tab 3 because this is the covered is discharged freely into the drainage. So that means there are no pressures in the covered. Okay, so the normal depth is less than the depth of the covered. Okay, so this is the question 6. Now question 7. The question 7, actually you can see that the storage patient is drained by a wheel with a crest length of 45 meters and the discharge coefficient is 0.6. So estimate the basin discharge when water is in the basin is 1.1 meter above the crest of the wheel. Actually, this is the broad crest wheel. It's a broad crest wheel. So we'll use the broad crest wheel equations. Okay, so we use the broad crest equations. So CD, the discharging coefficient is given, and the B and H and also given. Okay, let me see B. Basically, the crest length is 45 cm, and also the H is 1.1. Okay, means the water above the wheel. Okay, so we can easily find out the discharge. Okay, we can find out the basin discharge above the crest of the wheel, 0.92. 0.92. So next one is this question 8. So this question actually 500 millimeter diameter concrete drainage cover is to be placed on the roadway. So it is said that the water will pound behind the cover to a height 20 cm above the top of the cover. Okay, so if the covered entrance is to be well rounded and the slope is 2%, the length 20 meters, and the exit is not submerged, so estimate the discharge through the covered. So first you need to check whether the entrance is submerged or not. Okay, so firstly, let's have a look at this the solution of these questions. First, you need to check whether it is the H over D is larger than 1.2. The H is 0.7 over 0.4 over 0.5. So you can see it is larger than the 1.2. So we assume that it is the entrance is submerged. Okay, so that means it could be pad flow or orifice flow. Means it could be tab 2 or tab 3. Okay. Now we can use the we assume it is tab 2. Assume tab 2. Okay, so it is a pad flow. So the head loss is the is a loss in the at the entrance, friction loss, and the loss at the exit. Loss at exit. Okay. So we use this. Actually, this is we use the head loss equations. We use the head loss equations to find out the discharge. To find out the discharge rate in the covered. Okay, in the covered. So we can see that the at the entrance the coefficient is 0.05. I think it's given in this one in the questions. Let me see. Yes, given the entrance is 0.05. Okay, And also the let me see this one. The outlet is is 0. Means no means at exit is not submerged. Okay, the exit now is not submerged, so that means the so the exit matter loss is 0. Okay, matter loss is 0. So the HF is the friction loss. Friction loss we can get the friction loss here. Okay, because the L, D, and F are given. So finally, so we can find out the head change. Okay, the head change. So the head change, you can find out head change is 0.6. 0.6. The head change. So you can draw draw a graph here. Okay, to find out the change, the head of change, because it is 0.2 meters above the at the entrance. It is 0.2 meter above the top cover, and also we also consider the slope. Okay, the slope is 0.02 and 20 meters. The length is 20 meters. So we can find out the head change is 0.6. 0.6. So finally, you can see that the find out by using these equations. Okay, so this is the friction loss, matter loss. This is the head loss. Head change. Delta S means the head change. Head change. So the head change actually equals to the friction loss, matter loss, and also the head loss. The head loss. Actually, this one also is based on the Bernoulli equation. Based on the Bernoulli equation, actually, you can back to the Bernoulli equations. Okay, to find out this. This word, to find out this relations. So this is the head loss. So finally, we can get the velocity. That's 2.52. 2.5. So we can get the Q. The Q is 0.5 cubic meter per second, I think. And also, they still have another page. We need to calculate the discharge of the pipe if the pipe is full. When the pipe is full, we use the Manning's equations to calculate the discharge of the if the pipe is full is 0.54 cubic meter per second. So we can see that the full when the pipe is the pipe capacity, the pipe is larger than the pipe discharge rate. Okay, so that means the wear end is less than the diameter of the normal depth is less than the diameter of the pipe. Okay, less than diameter of the pipe. Okay, so we the orifice flow is confirmed. Okay, so that means it is not type 2, it's type 3. So this question actually will be a bit complicated, complex. So because it is first we try type 2, and finally we find out it is not type 2, it's type 3. So after calculations, we're using the type 3 equations. We could find out the discharge is 0.55. We need to further to check. Okay, the circular covered flow full when the discharge rate exceeds 1.07 Q full. Actually, because here you can see that the full discharge, the full capacity of the pipe is 0.54, but now if we use the orifice flow, it is 0.55. Okay, but as I mentioned that in the previous slide, that the circular covered the flows full when the discharge rate exceeds 1.07 Q full. So that means this is not full at this stage, at this case, in these questions. Okay, so now here actually this question actually not use the equations listed in the PPT slide. Okay, not listed in the PPT slide. Not in the PPT slide. So, and also you can use the you can use the equations listed in the previous slide. Okay, and also you can use the Bernoulli equations. To actually Bernoulli equation is comparing to the equations is relatively easier. Okay, easier. Okay. Maybe I just. Okay, it's fine. Maybe later I will show that. Now this is the questions. Any questions for this question? Is that clear? This question. Hello? Any questions do you have? Okay, it's fine. Now here's another here's the question. If the Q larger than Q full, it is type 2. As I mentioned that if you need to see whether it is circular covered, okay, circular covered, you know. So if it is a circular covered, actually it is the Q should be larger than 1.07 Q full. Okay, so if the Q larger than for the circular, I mean for the circular covered, if the Q is larger, means the discharge of the cover is larger than the 1.07 Q full. So actually it is type 2. Okay, it's type 2. For other types covered, for example, if the section is a square, it's a square section. So actually, if the Q is larger than Q full, so actually it is type 2. Okay, is that clear? Okay, so now means here you need to clear is the circular for the circular cover. Now this one actually is a concrete covered. Actually, it's a circular covered. So and also we can see the drainage, the discharge coefficient given, the entrance loss given, the slope given, okay, the length given, okay, and the water in the basin is 0.5 above the invert of the covered. Assume the covered exit is not submerged, and also if the pipe flow equation is applied, so the normal depth of flow in the covered is lower than the covered diameter. So actually, this question is you can check whether it is the entrance is submerged or not. So of course it is submerged. Then you need to check the exit. So you can see the exit is not submerged, right? The exit. And another important information is the normal depth in the cover is lower than the cover diameter. So which tab? Anyone know that for this question? Anyone knows? Yes, correct. Okay, yes, correct. So you can see that actually the exit is not submerged. Actually, it is not type 1, right? It is not type 1. So it could be type 2 or type 3. Okay, but another information tell us that the normal depth of flow in the cover is lower than the cover diameter. So we can easily know that it's type 3. Okay, it's type 3. Okay, good. So actually for type 3, it is easy. Okay, you can use the orifice flow equations to get the answer. Okay. Now this one, I will also ask you which is type 1, type 2, or type 3. The diameter, concrete cover, and also the discharge coefficient given, the slope given, the length, the basin discharge when the water in the basin is 1.5 meter above the invert. The exit is not submerged. And also we can see that this important information. The normal depth of flow in the cover is larger than the covered diameter. So it is type 2. Oh, yes, it's type 2. Yeah, correct. So because these questions, firstly, we need to see that to check whether the entrance, and first you need to check the entrance is submerged or not. Means the H over D is larger than 1.2 or not. Okay, so the H is the depth of the basin. That means the water in the basin, the depth of water in the basin. The H, the D is the depth of the covered, or the diameter of the covered. Okay, so if the H over D is larger than 1.2, so this entrance is submerged. Okay, now next you need to check the exit. Okay, the exit. If the exit is submerged, so it is type 1. So if the exit is not submerged, you need to check it is type 2 or type 3. Okay, we use the normal depth. Okay, with the normal depth. So actually these questions actually, and also question 9. So the normal depth, so in question 9, the normal depth is less than the covered diameter. So you can see it is type 3. But in this question, you can see that the normal depth is larger than the covered diameter. So that means it is type 2. So that means sometimes the questions will provide some information you can determine it is type 2 or type 3. But sometimes you need to determine that by your own calculations. Okay, so that is question 8. Okay, so the question 8 is showing examples. So that means you need to determine the type 2 or type 3 by calculations. Actually, this is this question is actually we also use the I just mentioned that we use the what's called Bernoulli equation. I just to repeat the Bernoulli equation. And the Bernoulli equation is very easy to use. Okay, compared to the equations provided. Okay. So because here you can see that this is the Bernoulli equation. This is the Bernoulli equation. So the Bernoulli equation means there are 3 types for a steady flow. For the steady flow at each sections, the sum. So the sum of the 3 types of energy is constant, remains constant. So that means what are the 3 types? What are the 3 types energy? Anyone remember? For the 3 types energy, for the Bernoulli equation, anyone remember the 3 types energy? Okay, the first one, okay, remember the first one is the pressure energy. Okay, this is the pressure. Okay, P represents pressure of energy. So V square over 2G. What is energy? What is this energy? Anyone know that? So this is kinetic energy. Okay, kinetic energy. So this is the kinetic energy. I will tap you the 3 energy. Okay. These are the three energies in the Bernoulli equation. The 3 energy in the Bernoulli equation. Pressure energy, the P. Okay, the P over the gamma. I think over the gamma is the pressure energy. So the V square over 2G represent the kinetic energy because it's moving and because the water is moving, flowing. Okay, so this is kinetic. So it has kinetic energy. Another is potential energy. Z represents potential energy. Means from high elevations to the low elevations. So the energy potential, the potential energy change, reduced. Okay. So this three energy sum, the sum of these three energy maintains constant. Okay, maintain constant. So actually, we need to know that the energy loss. Well, what we need to know is the energy loss. Okay, so in the cover, actually there are two types of loss. Two types of energy loss. One is the friction loss, HF. So HF represents the friction loss. Okay, friction loss. And another one. This one is called the Manner loss. Manner loss means the loss and loss from other sources such as the entrance, the exit, the band of the cover. Okay, and also any grills or bars used at the entrance. Okay, for example. Okay, or the manhole settlers. Okay. So all these are called energy loss. Okay, so we use the Km, the coefficients represent different types of the Manner energy loss. Okay, now is that clear with you? And also then the P1 and the P2, normally we see that the P1 and the P2 they no change. Okay, the pressure no change. Okay, pressure no change means releasing the water to the downstream areas, the water releasing to the downstream areas, and also the water in the basins, the pressure is the same because they all both exposed to the atmosphere, right? So they are all under the atmospheric pressure. Okay, so P1 and the P2 the same. Okay, and the V1 is the velocity at the entrance. V1. V1 is here. This is V1. Okay, V1. So V2 is here. So that means V1. We also now means we use the Bernoulli equations that we normally assume for the detention basin. We normally assume that the V1 at the entrance, the V1 is 0. No, 0. The velocity is 0. The velocity is 0. Means the velocity will become larger and larger to V2. Okay. Is 0. So that means this one also no 0. Okay, P1 and the P2, we can delete the P1 and the P2. So you can see that now only the Z1 and the Z2 left. Z1 and Z2 and the energy loss. So you can see very easily the head change. Means the water level between the water in the basin and also the exit, the water surface. Okay. The water surface. For example, if the water surface is here at the exit, so the head, so the head change. So the head change is this one. So this part is what is Z1 minus Z2. This part is Z1 minus Z2. It is also called the head change. So you can see easily find that the head change is the kinetic. The head change convert to kinetic energy and change to the energy loss. Okay, and change the energy loss. The head change. The head change means the head change because of the energy. The energy now the head change energy convert to the kinetic energy, and also they convert to the energy loss, friction loss, and also Manner loss. So very easily use the Bernoulli equation actually to put it in a simple ways for you to calculate. So you can easily find out the velocity here, and also to find out the Q, the discharge rate in the cover. So that it is 0.56. Okay, this one you don't need to check that because it is also mentioned that it is tab 2. But if you have interest, I would suggest you to check this one using the equations of tab 2 or tab 1. Okay. Using the equations. Okay, using the equations for tab 1 or tab 2, you can check whether the result is this one. Actually, it's the same. It's the same. Okay. Okay, now let's take a break. Okay. I need to drink some water. I have a break, and we're back at. Okay. Hello, everyone. Okay, good.
Okay, after a short break, we continue the workshop, and next I will ask you to attempt the questions in 2017 exam question 3B. Okay, so these questions, let me see. This one, okay. Question B, okay. So question 3, part B, okay. So this is okay. But first you need to, I give you so I give you 10 minutes to do that one. I think it's an easier one, okay. So attempt these questions, okay. Hello, anyone? Hello, can you hear me? Okay, now attempt this question, okay? Question 3, part B, 10 minutes. This question I think is easy. So anyone finish that? Okay. So anyone let me know you finished that one? So okay, I'm now going to for the weightings because this question is comparing is relatively easier because this question is can easily find out that it is type what? Which type? Anyone can tell me? Type what? Okay, X is not submerged, and the normal depth in cover is less than the cover diameter. So you can easily see that it's type 3. Okay, type 3. So that means you just use the equations for the type 3 equations um, to find out the answer for these questions. Okay, let me see the solutions. These are the solutions for these questions because we can easily see that this is this is used to check the entrance is submerged or not. Okay, so you can see the entrance is submerged. Okay, so the first next we need to check it is tab 1, tab 2, or tab 3. So because it is given or it's already given the questions, okay, the entrance, so the exit is not submerged, and also the normal depth is less than the diameter of the cover. Okay, so it is tab 3. So the tab 3, we can use this orifice flow equations to get the discharge rate. Okay. Okay, so if no further questions, we move on to the routing. Okay, to the routing. Okay, the week 9 is for the hydraulic routines. Okay, hydraulic routines. You made the exam questions, either the exercise. Let me see. Just close that. No, the answer is not this one. The answer is oh, let me see. 1.25 cubic meter per second. Okay, 1.25. 1.25. Okay, you can check that. But actually, anyway, I will upload the answers later. Okay, you can check that. Okay. Okay, let's move to the hydraulic routine. Okay, hydraulic routine. So the hydraulic routines has been used for many years. Okay, so in generally, the hydraulic routing methods include the simply find numerical techniques. Okay, conservation of mass and steady flow hydraulics. And also the hydraulic routing methods require relation of the discharge and the storage in the reservoirs. Actually, it is depends on actually. Okay, for the hydraulic routing, actually, you can see that it depends on the volume of the flood and storage, and also the relative the physical characteristic of the storage. So the relation actually could be linear. Okay, the method could be linear or nonlinear. Linear or nonlinear. So actually, it is important in the hydraulic routing. Actually, is important in the design of dam spillways, the retarding basins in the urban area, and also the forecasting of the flood, and the evaluation of the flood mitigation and flood estimation, and also transferring the flood effect from one area to another one. Okay. So actually, there are numerical techniques we can use, okay, to calculate the changes in the hydrograph. So the change in the hydrograph as observed through delays and reductions in the peak flow, and also the reservoirs actually is a body of water, so with the flood water surface such as lake dams and stormwater basins, etc. Now, how can we see from the continuity equation? So the change in the storage basins is inflow minus outflow. Okay. So it's quite easy to understand, right? The change in the storage is inflow minus outflow. Okay. So if we take take the time, a small time, okay. If we take a small time dt, so you can see the storage change over the time dt. So the ds over dt is the change in the storage. So it's equal to the it minus qt. It is the inflow, qt is the outflow. Okay. So over the time between t and t plus delta t, means if there are time change delta t. Okay. So the above continuity equation can be written as the following. Okay. So that means this is the change of the storage during the time delta t, during the time t1 to t2. Okay. So and also the storage change is equal to what? Is equal to the inflow minus the outflow. Okay, between the time t1 and t2, because the So the inflow between the time T1 and T2, we use the average, okay? And also the same between the T1 and T2, the outflow, we also use the average, okay? This is also easy to understand, right? Okay. Then we arrange this one. So we arrange this. We rearrange this equation, so we can see that the I1 plus I2 plus 2S1 over delta T minus Q1 is equal to 2S2 over delta T plus Q2. Okay. So actually, this is used can be used to help us to do the hydraulic routing Okay, because the known quantity is time t and I1 and I2 from the inflow hydrograph. Okay, so the I1 and I2 working is also known, okay, from the inflow hydrograph, and the Q1 and S1, which are initially 0. Okay, S1 and Q1 actually at the beginning is 0. Okay, at the beginning is 0. Then S1 and Q1 are known from the previous time. Okay, from previous time. Okay, so Q2 and S2 are unknown. Okay, so we need a second equation. So that means in this equation, actually, the left side is unknown, but the right side unknown, and also there are two variables S2 and Q2. So we need another equation. So from this one, we can see that we can generalize that. Okay, use n between n and n plus 1. It can be seen that the how can we choose the time interval delta t? Okay, delta t. Normally there should be at a minimum 5 to 6 points on the rising side. Okay. Okay. And as I just mentioned that the I1 and I2 are known at every time step because the inflow they are known from the inflow hydrograph. So for the uncaged spillway, orifice tap outlet and the weir tap outlet, so the outflow actually is no function of the stage in the reservoirs. Okay, because we just introduced the 3 types of the outlet structures. Okay, open channel, orifice channel, or I'm sorry, open channel, orifice, and also the PEP, even the PEP, and also the weir tap outlet. So we can find out that the outflow is the function of the stage. Means is the function of the H in the depth of water in the basin. So this is another one. So this is another equation. So now we have 2 equations, 2 variables, 2 unknown variables. Okay. So the storage is typically known as a function of the stage H in the reservoirs. Okay. So Q and S initially set as 0, then we can get that from the previous time period. Okay. So how about n plus 1? Q and S n plus 1 means they're at are unknown, right? So actually they can be determined from the known functions of the stage. Means they can be represented by using the functions of the stage. Means using the function of the H. Okay. So the here is the reservoir function. Here's the reservoir function. Okay. So the continued equation is showing the unknowns as a function of nodes. Means unknowns is the this side is the unknown. The left side is no. The left side is no. So the reserve function actually depends on the type of storage and the data available. Okay. So we can plot the elevation above basin floor level with S. Okay. And also the storage S for various H above spillways, we can get Okay, and also find the Q and H relationship. Actually, normally this is from the hydraulic model. Okay, now from 1 to 2, okay, from 1 to obtained in the S and Q. From 1 to 2, I can get S and Q, means from previous ones. But actually, it is you may not still very clearly understand the steps, but actually we can use the examples to illustrate how to do the hydraulic routings using the reservoir equations function, using the reservoir function. So this is the stormwater detention basin. Okay, so actually this is a stage and a storage table showing the relationship between the stage and the storage. Okay, based on the data, based on the geometry of the basin, of the storage basin, and also the flow, the discharge from the discharge weir from the detention basin, and the stage also given, and the stage is also given. So it's given. It's also given. It's also given. So and also the runoff hydrograph is given. Means the inflow hydrograph is also given in this table. Okay. So if the pre-storm stage in the detention basin is 5, so estimate the discharge hydrograph solution. Use the time 30 minutes interval. Okay. Now this slide is actually showing the hydraulic routing method. Okay. Now let's have a look at. Now, firstly, we need to have the properties, the reservoir properties, to listing the relation between the stage and the storage. The stage between the stage and list the relation between the stage and storage, and the stage between the discharge, stage between charge. So we can get the 2s over delta t plus q. Okay. So we list this all in the table. We list this all in the table, and also we can draw a graph. Okay, let me see, we have a graph. Yeah, we can draw a graph between the Q and the 2s over delta t plus Q. Okay, draw a because it is actually this Q, these two, the relation between these two actually is normally is not linear. Actually, normally it's a non-linear relation. It's a non-linear relation. Okay. So normally we can use a graph paper to draw the relation between these two. Okay, so they can see the step. The first step, we tabulate the inflow hydrograph in column 1, 2. Okay, 1, 2 here. Okay. So the first row represents the time 0 is given by the initial conditions. So we can see that for the first row, the the columns, the 2s, the s, and the q are all 0. Okay, so that means for the first row, all these are 0. All these are 0. So next, we move time 30 minutes. We move the time 30 minutes. For 30 minutes, the I1 is 0. So I2 is 2.4. 2.4. So we can get, and also we can see that this one 2s1 over delta t minus q1 is 0 because this is from initial station, initial condition. Initial condition, the S1 and Q1 are 0, both are 0. Okay, so we calculate the 2s2. We can calculate the 2s2 over delta t plus Q2. Means this is the next stage. This is the next stage. Next step. This is the next step. The value. So the next value is I1 plus I2 plus 2s1 over delta t minus Q1. Okay. So you can see that I1 plus I2 is 1. It's 0 plus 2.4, right? So this 0 is I1, I1 plus I2. So I1, I2. Okay. So how about this part? This part is 0. This part, because the initial value is 0. 0. So we can see that it is 2.4. 2.4. So we can written in column 4 at a time 30 minutes. So that means you can see that here is 2.4. So that means the arrow showing the how to get this value. Okay, so actually this value is from I1 plus I2 plus this one. I can get this one. Okay. So how to get the Q? Because we get a Q from the graph, from this graph. Because this is 2.4, 2.4 here. Okay, because the 2s over delta t plus Q is 2.4, right? 2.4. Now we can estimate the Q here. The Q is around how much? 0.7. I'm not sure. 0.6. This is 0.68. 0.68. Okay. So the corresponding outflow Q2 is interpolated from the property 0.68. It's written in the column 5. So and also I would suggest, and also in the assessment, actually maybe it is suggested you use a graph paper. In that case, use a graph paper. Okay. So next we can get the we can get this one. We can get this one. Means the 2s over delta t minus q. We can get this one. We can get this. How to get this one? This means this one is this one minus 2 times this one. We can get this one. This one is 2s2 over delta t plus q2 minus 2q2. So that means 2.4. That means 2.4 minus 2 times 0.68. So we can get the 1.04. 1.04. So that means from here we can get this one 1.04. Okay, so then repeat the process. Okay, now 2.4 plus 5.6 and plus 1.04 can get 9.04, and then from the table can get the Q 4.26 and 9.04 minus 2 times 4.26, so we can get 0.52. Okay, etc. And now repeat the step, repeat, and also until the outflow is 0. Outflow is 0. So we can find out the outflow of the weird, Okay, so finally you can see that the outflow peak now reduced to 4.53. Originally the peak flow is here. This is the peak flow for the inflow hydrograph. The peak flow is 5.6, but now reduced to 4.53, and also the time delayed it 30 minutes. Time delayed 30 minutes. Okay, any questions? Question you have by using this this hydraulic routing method? Hello, any questions? Okay, good. Now, let's estimate the basin properties. Okay, now we have the inflow and outflow, so we can easily to find out the SP. So SP is the maximum volume of the storage for the storage of the storm water. Okay, so the SP is the 1 minus QP over IP times the V in. Okay, we just mentioned about that. And also make sure that the QP is the peak discharge rate of the outflow. So that means the QP should be less than pre-development peak by using the rational method. Means the QY is from the based on the rational method. So if there's not enough storage in the detention basin to accommodate SP volume, so we need to adjust the size of the detention basin. So actually now we have still some exercise. Let's I just show you some of the exercise. For the exercise, for questions 11, 12, I think it's 11, 12. Now this is the question 11. Question 11. Okay, so you can see this is the detention basins with the outflow weird. Okay, so the division and the storage relation is shown here. Okay, so it's one. And also the discharge, and also stage is showing here. Okay, discharge and also the stage is showing here. and also the inflow hydrograph is a given, inflow. So how to to ask the maximum discharge, from detention basin. So that means you need to use the hydraulic routings to get the outflow hydrograph. Okay. So now let's look at the solution for this question. How do we find out this the maximum discharge from the detention basin? Okay. Now, firstly, we need to find out the properties, the reservoir properties, Now, we can list that in table first, like elevation, storage, and the Q, and the 2s over delta T plus Q. So list them in the table. Okay. So with the table, why we need a table? Because we can draw that in the graph. Okay. We need to draw that in the graph. Okay. We draw this. So we draw this relation between Q and between these two. We draw the relation between Q and 2s over T over delta T plus Q in this graph paper. Actually, you can see that it's a nonlinear relation. Okay, it's a nonlinear relation. So it will be more accurate. It will be more accurate if we use a graph papers because they not really non-linear relationship between these two. Okay, so after that, what we need to do is to using the list the time here, and also list the inflow here, and also we use the reservoir function, Okay, the reservoir functions to do the hydraulic routing. Okay, start from the start from T0. So all initial conditions are 0. Okay, then we start from to I1 plus I2. And so we can get this one, I1 and I2. We just have a look at I1 and I2 plus and plus this one. So we can get what? So we can get this one. 50. Now, after getting 50, we need to get the Q. Q is from the curve. Remember? Okay. From the graph, we use the graph paper to plot the relation between these two. So we need to find out this one. Okay. Now then we back to get 48. 48. How to get 48? 48 is what? Is 50. Is 50 minus 2 times 1. 2 times 1. So that is 48. Then we move to the next step. I2 plus I3. So we can get and plus this one. So we can get this one. Okay. Now in the graph, in the curve, in the graph, we will find out the Q. Okay, this one, and then we back to this one. Okay. So that means 218 minus 2 times 5. Okay, find 208. Okay. Then we move to the next one. And repeat the next until this the outflow is 0. Okay, but actually this question is this question does not ask you to plot the outflow hydrograph, so you don't need to do that, because you need to. I think you may need 10 more steps at least. Okay, so this question is ask you to find out the maximum discharge. So you can easily find out the maximum discharge is here, 38. See that? Okay. The maximum discharge is 38. So how about the inflow? The inflow, the maximum is 160. 160. So you can compare actually the peak flow discharge. The peak flow actually inflow actually reduced. Okay, a lot. Actually, I reduced a lot. Okay. So any questions do you have for this question? Have any questions? Hello? Okay, now we move to the next questions. Next questions. Here's another. We stop the at step 5, right? So actually, it depends on what are the questions asked. Okay. So if you are asked to determine the maximum, so that means you need to make sure that you already have the maximum. Okay. So I would suggest that you after the maximum discharge you have, you can calculate further at least three steps. Okay, I would suggest that. Okay. But if the question is asking you to, for example, to plot the hydraulic outflow hydraulic graph, so you need to finish until the outflow rate is 0. Okay, is that clear? Okay, good. Now let's look at the next questions. Next questions is question 12. Question 12. So so the inflow hydrograph is given here. The inflow. Okay, and it's a vertical wall detention basin, has a surface area 5 hectares, and the emergency spillway width 30 meters, and the weir coefficient is 0.66. Actually, this is not weir thing. I don't like this weir coefficient. Actually, it is discharge coefficient at 0.66. Okay. So determine the relationship between the height of water above the weir level and the detention basin storage. Because this is a vertical wall detention basin actually, and our surface is 5 hectares. Actually, it is very easy to calculate that. Okay, it means the area, surface area times the height, times the height above the water level, and determine the relationship between the spillway discharge and the corresponding H value is given. So we'll use the weird model. Okay, so we'll use the weird model. Broad crest weird the equations. Okay, and what is the maximum discharge? Okay, and assume the inflow and outflow initial is both at 0. So actually, this is also we use the hydraulic routings to determine the hydraulic outflow hydrograph. Outflow hydrograph. So let's look at the solutions of these questions. Actually, similarly, we need to have the reservoir table, reservoir property table. Okay. For these questions, we need to calculate the relation between the stage. Okay, we need to calculate the relationship between the stage. Okay, between the stage and the volume. Okay, and the Q, and also we need to get the QS 2S over T plus Q. How to get the Q? Actually, we use these equations. I also show you in the previous slides. Okay. So, and also with the Q and with the value of these two columns, with the value of we can plot them in the graph paper. Okay, we plot them on graph paper. Okay, plot them on graph paper to show the relation between these two. Now next, we can use the hydraulic routings. We can use the hydraulic routings to get the outflow hydrograph. Outflow hydrograph. Now the time, the inflow hydrograph, the 2S over delta T minus Q, the 2S over delta T plus Q, and this is Q. Repeat the same step. I1 plus I2 plus this one. Okay, we can get this one, 2. Okay, now from the graph, we can get this one. Okay, and then back to this one. Okay, then I2 plus I3 plus this one. So we can get this one. Okay, then from the graph, we can get this one, and then back to this one. How to back to this one? I mean 9 minus 2 times 2.5. Okay, easily. Now repeat the process. You can play this this routing. I can play the routing until the outflow is 0. So finally, you can see the maximum discharge is here. Maximum discharge here. Okay. So any questions? Have? Okay. Okay. Good. Actually, there's another questions about exam papers. I think we do not have time to do that in the workshop, but I will show the answers. Okay. So this question actually is I can show here actually is part C. Part C. So in this question, you can see that the this is the stage and the stage in storage. So you can see in table 3.1. So this is the stage and also the storage stage and storage. So how about stage and the discharge of the weird? So it's given by use this formula. Okay, by using equation. By use this equation. Okay, so that means you need to get the Q and the 2s over T plus Q in the table, and also plot on the graph paper. Okay, so then the inflow hydrograph is given here. Okay, so you will do the routings. So show the solutions. I think it is quite similar to the previous questions, the steps. So as I mentioned, the first step you need to do is to the first step you need to do is to plot the reservoir information, to plot the reservoir property in a table. Okay, the stage here, the stage, storage, the Q, and the 2s over delta T plus Q. Okay, and then with the value in these two columns, okay, you plot them in the graph paper. Okay, represent the ratio between these two. Now you list the table, the time inflow, 2s over delta T minus Q, 2s over delta T plus Q and Q. So for the routing purposes, okay. I1 plus I2 plus this one. Okay, you can get this one. Okay. Then from the graph, I can find out the Q. Then back to this one. Okay. Then the I2 plus I3 plus this one. You can get this one. Okay. And also from the graph, you can get this one. Okay. And then back to this one. Finally, you can see that the peak discharge, the maximum discharge is this one. So after that, you can plot them on the graph paper of course also. I can plot the outflow hydrograph on the graph paper if required. Okay, if required. Okay, so this is the. Okay, any questions? Okay. Almost done. So we normally there are three major parts as I mentioned beginning. So the first one is the rational method, and then we also introduce the time area method, and also the routines. Okay, any questions about the routines? Okay, great. Now week 9. Let me see week 9 and week 10. Week 9 and week 10, I think it's about the week 9 is about the water quality and water sensitive urban design, and week 10 is about pollutant reduction techniques, and also we also have a bio retention based design or rain garden design. So I'm now to go details of this part. Okay. Okay, now question time. Okay, so I think we already now have the revisions of the of the contents, okay, have been delivered in the covered in this course, okay. So and also for the calculation parts, actually, you may pay attention to the rational method, time area method, and also the 3 types of the cover flow, means type 1, type 2, type 3, and also the hydraulic routing. Okay, the question time. Okay, so you have any questions before we can close today's workshop? You can text the questions if you have, okay, in the chat room. Hello, any no questions? After the workshop, actually, I will upload the workshop PPT and the revisions and also the tutorial. I mean the tutorial questions, answers. Upload them to the Canvas for reference. Okay, for reference. I would upload them to the workshop folder. Okay, I'll upload them to the workshop folder. Okay, all this material to the workshop folder. Okay, on the Canvas for easy reference. Okay, I just will ask one more time. Any students have questions? If you do not have any questions, I would like to conclude the workshop. But actually, we still have a few minutes. If you have any questions, so please let me know. You can text your questions in the chat room, in the chat functions. Any students have any questions? Okay, now if no questions from you, actually, I would like to conclude the workshop. But actually, if you have any questions, you can send me email. Okay. Hello. Okay. So thank you for attending today's workshop. Okay. Thank you all. So bye. I will show you my email. Just wait a minute. You see my email address? Okay. Okay, great. Thank you all. Bye.